Hello, my name is Stephen Ferguson and the title of my webinar is PAT-based design of plug flow crystallizations. I carried out this research as part of my PhD in Professor Brian Glennon's research group, which is part of the Solid State Pharmaceutical Cluster at University College Dublin in Ireland. Before moving on, I would like to thank Mellor Toledo for giving me the opportunity to present my research in this webinar. So, the central objective of this work was to investigate the characterization, design and operation of plug flow crystallization in order to develop the required understanding to allow its application to industrial processes. In order to realize this objective, I went through the following steps, which I will go through sequentially over the course of the presentation. So firstly, I developed a plug flow crystallization platform and associated in situ measurement techniques. Following on from this, I applied these techniques in order to characterize the plug flow crystallization of benzoic acid. Then I assessed the effect of mixing ancillary rheology on this process, and finally, I compared the performance of the plug flow with the most common alternate crystallization methods in order to get a genuine assessment of its impact. To begin, I'll compare the respective concentration profiles for a typical anti-solvent crystallization using fed batch, plug flow, and MSMPR modes of operation. From the graph, it is obvious that the three crystallizer types offer very different process dynamics to one another. This allows alternative operating conditions to be accessed, which in turn allows crystal product to be generated that could not be produced if only batch production is considered. In this presentation, the focus on using these dynamics to manipulate CSD, particularly in terms of using plug flow crystallization to generate small crystal size distributions in order to negate the need for milling operations. However, the ability to isolate alternate polymorphs or avoid oiling out or other problematic secondary processes should also be possible. Visualization of crystallization dynamics is a good way of identifying the advantages and limitations of each methodology. For example, in the case of the standard fed batch crystallization, anti-solvent addition rate is often used as a parameter to manipulate the final product crystal size distribution. Faster addition rates increase the metastable zone width. This results in a higher proportion of the solute mass initially crystallizing via nucleation. Subsequently, the product crystal size distribution contains a larger number of crystals of smaller mean size. However, in systems with fast enucleation kinetics, the metastable zone width can be very narrow. In such situations, the extent to which this method can reduce the product crystal size is limited. This contrasts to the plug flow crystallization, where the feed and anti-solvent streams are mixed directly to the final solvent-anti-solvent concentration. As such, the concept of a limiting metastable zone really isn't applicable. If the feed and anti-solvent streams can be assumed to be perfectly mixed, a single addition plug flow crystallization, such as this one, generates the highest possible supersaturation for a given feed concentration, thus maximizing the amount of initial nucleation and ideally producing the smallest crystal size distribution possible for a given set of operating conditions. The remainder of the supersaturation is then depleted in a subsequent tubular section with the required residence time and hence the size of this section dictated by the kinetics of the system. As such, the dynamics of a plug flow crystallization are mathematically identical to that of a non-fed batch, except that supersaturation is depleted along the length of the tubular section rather than with respect to batch time. This contrasts to the MSMPR crystallizer, which operates ideally at steady state with respect to both position and time. The focus of this work is mainly on the application of in situ process analytical technology in order to develop an efficient and robust design methodology for industrial plug flow crystallizations. However, the performance of the plug flow will be compared to that of both batch and MSMPR crystallizers for the anti-solvent crystallization of benzoic acid, a model organic compound, so that a genuine comparison of the impact of plug flow crystallization can be made. The figure on the left-hand side is a schematic representation of the plug flow crystallization platform. As highlighted previously, all runs were carried out using an initial 100% anti-solvent charge. Subsaturated feed containing benzoic acid in aqueous ethanol solution is pumped from a feed tank and is brought together with an anti-solvent stream, which in the case of this system is pure water. The two streams are mixed together within a Renton-type vortex mixer, a schematic and image of which are shown on the right-hand side. Once mixed, the solution enters a subsequent tubular section, 2.9 mm in diameter and of variable length. Observations of the crystallization are carried out in situ via flow cells designed to accommodate FBRM, FTIR and PVM. The residence time at which the crystallization is observed can be varied simply by changing the length of the tubular section. The system can then be cleaned in place between runs, allowing for negligible turnaround time. The resin mixer geometry is perhaps the most important aspect of the crystallizer design. It is essentially a vortex mixer with two inlet streams entering tangentially to the wall, both in the anti-clockwise direction. Unlike the more common confined impinging jet mixer, it maintains mixing efficiency without the requirement to balance inlet flow rates. Operationally, this is highly advantageous. For example, in circumstances where a 10x anti-solvent charge is required in order to maximize process yield. In addition to this allows higher supersaturations to be accessed, allowing for further reductions in particle size if required. The final thing to note is the level of productivity. Despite having a volume of approximately 33 milliliters, the plug flow device is capable of producing 60 kilograms a day of dry, isolated benzoic acid product, essentially providing industrial scale pharmaceutical production with lab scale equipment. The photograph on the top right shows the experimental rig with the FTIR in situ. The white object on the left hand side is a flow cell and is capable of accommodating the FBRM and FTR simultaneously or one at a time. The photograph below this is the PVM flow cell. Crystal size was measured in situ via FBRM core length measurements, with offline microscopy used in order to confirm the observed trends. Concentration was monitored in situ using the calibration-free peak tracking method proposed by Barrett et al. This allowed information on the process to be obtained immediately. In the case of the plug flow crystallizer, it allows an intuitive method of qualitatively monitoring liquid phase solid concentration. This is significant due to the position of the crystallizer far beyond the metastable limit on the phase diagram, making the creation of a calibration model extremely challenging and will require a huge extrapolation from the calibration dataset in order to quantify experimental measurement. So far, I've described the experimental rig and analytical techniques, and so now I'll apply these methods in order to characterize the anti-solvent crystallization of benzoic acid. But first, if given a new compound, how can I tell if it will be suitable for plug flow? Well, initially you can carry out a simple test that takes advantage of the similarity in dynamics of the plug flow and a pure batch crystallization. So to do this, a single 100% anti-solvent addition is carried out into a batch vessel. The time required for the system to nucleate and reach completion is measured using FBRM and IR. This approximates the residence time required for the equivalent plug flow crystallization and therefore the required size of the tubular section. The figure shows the results of this test for benzoic acid. Initially, a clear undersaturated solution is present in the batch vessel. After the anti-solvent is charged, it can be seen from the FBRM counts that nucleation occurs almost immediately. The benzoic acid is then depleted in approximately 15 seconds, reaching the saturation value. Assuming that a minimum Reynolds number of 4000 is sought, the required tubular section will be 20 meters in length, which is clearly suitable. This contrasts to another API with much slower growth and nucleation kinetics. In this case, a reverse addition was carried out in order to maximize the initial supersaturation. However, it can be seen that after adding the feed solution, it takes almost 3 minutes to nucleate and a further 6 to 7 minutes to reach saturation. Using the same metric as applied to the benzoic acid test, this would require a tube of approximately 900 meters in order to allow the crystallization to reach completion, and hence is not really a viable candidate for this type of plug flow crystallization. Once you have established that the system is suitable for the plug flow, you can set about characterizing and optimizing it. Most basically, you want to find out when the process will reach steady state and what is the product quality at this point. This is trivial when in situ observations are available and simply involve placing the PAT flow cell at the crystallizer outlet. The FBRM and FTIR data for a typical run is shown in the graph. This information can be seen live during an experiment and indicates when steady state has been reached. Initially, the instruments read background noise and spectra for IMS, which is used to clean and prime the system between runs. The time to displace the IMS is the limiting factor in reaching steady state, but in spite of this, it is achieved in approximately 30 seconds. The rapid progression to steady state, combined with the small volume of the system, means that although the plug flow may be sufficiently productive for industrial scale pharma applications, the amount of material required for characterization will be similar to that for current batch process development. Therefore, it may be possible to avoid scaling up altogether and possibly introduce numbering up of units if additional capacity is required. In addition to monitoring the crystallization over the course of a run, its progression with respect to residence time is also easily measured in situ. In the tubular section, residence time increases with length, and hence the progression of the crystallization can be monitored by incrementally increasing the tube length and taking the steady state values at each point. By doing this, we can track the benzoic acid concentration decrease to the saturation value, allowing us to determine the required length needed to maximize the yield for the crystallization. Similarly, the increase in mean core length can be used to track crystal growth to its terminal value. Once the required crystallizer volume has been determined, in situ PAT can be used in order to empirically characterize or optimize the process. Plug flow crystallizations, such as this one, are suited to producing small and narrowly distributed crystal size distributions in order to meet bioavailability requirements for formulation without the need for milling. However, once these requirements are met, further reduction in mean crystal size may unnecessarily impact on downstream processing. In situ FBRM allows rapid process characterization so that an optimal crystallization design in terms of crystal size, downstream processing, and maximizing productivity can be found. As discussed earlier, the route and mixer design allows uneven inlet flow rate ratios to be used. This enables the initial supersaturation and hence the product crystal size distribution to be manipulated even when the solid concentration of the feed stream cannot be changed. This simply involves altering the relative flow rates of the two inlet streams. In the case of the benzoic acid system, this approach allows the dialing up of a required particle size. The graph shows the normalized, unweighted and square-weighted FBRM chord length distributions for runs with a fixed feed concentration but with the relative anti-solvent to solvent, or in this case water to ethanol ratios, increased from a value of 3.1 to 7.3. When the relative anti-solvent flow rate increases, both the square-weighted and unweighted chord length distributions shift to the left, indicating a decrease in mean crystal size. This trend is confirmed by the PVM images, which show a shift from a distribution of some fines with larger, more needle-like particles to a distribution nearly exclusively of fines below 10 microns in length as the anti-solvent ratio is increased. While the route and mixer does provide reasonable scope to manipulate product crystal size with a fixed feed concentration, if larger or smaller CSDs are desired, it is necessary to change the concentration of the solute in the feed stream. This allows higher initial supersaturations to be generated and hence product crystal sizes to be reduced further. This is the method employed to control the CSD in confined impinging jet crystallizations, where the inlet flow rates must be balanced in order to maintain mixing efficiency. But again, the extent to which the particle size can be reduced will depend on the kinetics of the system. The two chord length distributions below outline the extent to which the benzoic acid product crystal size can be controlled solely by manipulating the anti-solvent and feed stream flow rates at a fixed feed concentration. The red and blue chord length distributions represent runs carried out at the same anti-solvent solvent composition as the purple one, except with a significantly higher and lower benzoic acid concentration in the feed. This increased range of initial supersaturations results in a corresponding increase in the attainable range of product crystal sizes, with the square-weighted FBRM mean statistic shifting from 28 to 106 microns from the high to low feed concentration runs. This is perhaps illustrated more dramatically by the corresponding microscope images. However, it should be noted that organic compounds such as benzoic acid do not readily form nanoparticle distributions, and as such, increased supersaturation or feed concentration will have a diminishing effect on CSD as this limit is approached. Operationally though, further increases in concentration may improve process performance by increasing solids concentration and hence the productivity, provided the flow rates can be maintained. In fact, pressure drop is ultimately the limiting factor on the productivity of the crystallizer. But still, the plug flow offers an extremely intensive production methodology, with the 33 milliliter crystallizer producing over 60 kilograms a day of dry isolated benzoic acid. However, the pressure drop of the benzoic acid slurries showed some unusual behavior across the tubular section. As would be expected, pressure drop was negligible for water and the clear saturated benzoic acid solution until a Reynolds number of approximately 4,000 was reached. After this, a gradual increase in pressure drop was observed with flow rate after the onset of turbulent flow. When solids were present in the flow, the pressure drop across this section was higher than expected, despite the relatively low solids loadings, and particularly at lower, more laminar flow rates. This indicates that significant fluid particle interactions are present in the flow. In fact, small particulate slurries can often exhibit viscoplastic behavior that can impact strongly on the flow. For this reason, the generalized Reynolds number analysis was applied in order to determine the prevailing flow regime and the effective properties of the two-phase flow. This analysis indicated that the highest generalized Reynolds numbers obtained were well below the consensus values for the onset of turbulence. This was surprising given the fact that the standard pipe flow Reynolds numbers were as high as 10,000 for the experimental runs. Also, the presence of fine particulates seemed to induce effective shear thinning behavior in the two-phase flow. This analysis can be used directly for scale-up calculations. However, great care should be taken as it assumes time-independent behavior with respect to pressure drop, which, although true for this crystallization, may be violated by the progression of others. The final important design consideration for a plug flow crystallization of this type is the effect of mixing. At the high supersaturations used in these devices, crystallizations can often be mixing limited in spite of the rapid mixing times provided by the Rowden and similar mixer designs. The dam collar number has been suggested as the controlling factor in this process and is simply the ratio of the mixing time in the Rowden mixer and the precipitation time scale for the crystallization. The figure below schematically shows the effect of mixing on mean crystal size. At lower jet Reynolds numbers on the left, the system is mixing limited, but as flow rates, and hence the jet Reynolds number, is increased, the mixing time drops and with it the mean crystal size. This continues until a dam collar number of 1 is reached, at which point the crystallization is free from mixing limitations, and a minimum or plateau in the crystal size for that experimental concentration is reached. The photographs on the right hand side show passive tracer and benzoic acid crystallization runs within the Rowden mixer. The encircled mixing chamber has a residence time of approximately 16 milliseconds for each of these runs. It is clear that both the mixing and precipitation timescales for this system are extremely fast, with the induction time for nucleation seemingly taking less than 5 milliseconds. A simple global mixing model based on the energy inputs into the system is used in order to attempt to get an order of magnitude estimate of mixing time. The current standard in determining mixing timescales for the Rowden mixer is computational fluid dynamics, which has been shown to accurately predict average mixing times using the standard kappa epsilon model with enhanced wall treatment. However, neither this nor the simpler average model can account for the effect of fluid particle interactions in the benzoic acid slurries, and hence there will be significant uncertainty with both methods. For this reason, the simpler model is preferred here. The graph below shows the reduction in residence time in the Rowden mixer as a function of jet Reynolds number as the total flow rate through the crystallizer is increased. Overlain is the mixing time predicted by the global mixing model. This indicates that the mixing of the feed and anti-solvent streams are not complete within the mixer volume, and implies that the crystallization is mixing limited at all flow rates used. This is consistent with the findings of the crystallization runs, where the FBRM mean chord length was found to decrease with increasing Reynolds number. However, even at the maximum rate of throughput, the mixing was not sufficiently fast to reach the minimum plateau in crystal size that would show that the crystallization was free of mixing limitations. This finding highlights the importance of reliable measurement techniques, as despite the fact that non-ideal two-phase flow and imperfect mixing were found to occur, the in-situ application of PAT provided a fast and robust method for an empirical design that can easily account for non-ideal system behavior. As outlined already, the small volume of the system and the rapid attainment of steady state may even allow for empirical optimization at scale. Now that the PAT-based design of the plug flow crystallization has been outlined, I will briefly compare its performance to the most common alternate methods, namely fed batch, batch reverse addition, and MSMPR crystallizations, so that a true assessment of the impact of plug flow crystallization can be made. For the purposes of this comparison, both the feed concentration and the end point of the benzoic acid crystallization will be fixed. In spite of this, the alternate process dynamics allow different crystal size distributions to be accessed. The MSMPR runs were carried out in the Mettler-Toledo Optimax system, which was modified in order to allow pneumatic slurry transfers. Product withdrawal was carried out intermittently with the rapid periodic removal of up to 12% of total slurry volume. The FBRM was successfully applied in situ to track the attainment of steady state and also to compare the product CLDs for runs with various experimental conditions. Both fed batch and batch reverse addition crystallizations were carried out at the smaller 100 ml scale in the Mettler-Toledo EasyMax system. The calibration-free IOR methodology proposed by Barrett et al. Was used in order to track the concentration profiles for the batch runs, with the FBRM used to monitor nucleation growth and to measure product chord length distributions. The FBRM chord length distributions and associated statistics represent the final product slurries for each of these methodologies. The solids concentration in solution is approximately equal for each of these runs, as the feed and final anti-solvent solvent compositions are both fixed. Interestingly, the smallest and largest crystal size distributions, as represented by the FBRM size and number statistics, correspond to the two continuous crystallization methodologies. This indicates the potential of continuous production to allow material that cannot be generated by batch crystallization to be isolated. In addition to this, continuous crystallization, and particularly plug flow, have dramatically improved productivity. For example, the same amount of material is produced on a per annum basis by the plug flow run or 42 10,000 litre batches. This can be achieved using a 9 litre MSMPR crystallizer also, and assumes that 300 days of operation per year are conducted. Offline microscopy was used to validate the FBRM observations for each of the crystallization methods. Surprisingly, the MSMPR produced crystals that had different morphology to the batch runs, with three-dimensional steps growing on the crystal surface. This produced jagged, uneven particles when compared to the flat elongated plates from the batch crystallizations. Such behavior cannot be foreseen across the various production platforms using predictive modeling. Again, this emphasizes the importance of robust empirical design methods. The product crystals from the plug flow were too small to compare the levels of magnification used for the other methods. However, the huge reduction in particle size is clearly shown by the comparison of the in-situ PVM images for the batch and plug flow crystallizations. So finally, just to sum up the main points of the talk. Well, firstly, plug flow crystallization enables the production of a small, narrowly distributed product CSD without the need for milling. This was achieved by utilizing the dynamics of the plug flow in order to access supersaturations unavailable in batch crystallization. More generally though, the dynamics offered by continuous crystallizers may also allow alternate polymorphs to be isolated or problematic system behavior to be avoided. In addition to this, the plug flow system was found to be highly productive and attained steady state very rapidly. Potentially this may allow industrial scale pharmaceutical production with lab scale equipment, and consequently negating the need for scale up. Finally, the in-situ PAT-based empirical design can account for non-ideal process behavior in addition to significantly reducing process development time. It is hoped that this can facilitate the inclusion of continuous crystallization into standard pharmaceutical process development procedures. I would like to acknowledge all of the members of the Glennon Research Group for their help over the course of my PhD, Particularly I'd like to thank Professor Glennon and the postdocs Mark Barrett and Hong Sung Hao. I would also like to thank Gary Morris for his help with the experiments included in this talk. Finally, I'd like to thank the Solid State Pharmaceutical Cluster and Science Foundation Ireland for supporting this research and funding.